Good evening, everyone. Since I want to actually try and start on time, so that way we get through everything that we need to get through tonight. A couple of good presentations, and that way you don't have to listen to me talk all night long. So welcome to our November meeting of the Minnesota Astronomical Society. There is a picture on your screens that Larry Kane sent to me of the eclipse. And I think it's very, very cool and interesting. Larry, would you be able to talk a little bit about it?
Sure. Yeah, I went down to Albuquerque for the eclipse.
See online. Okay.
And can you hear me?
All right. Okay, now we can. Matt just had to turn up the volume.
Okay. Yeah, I went down to Albuquerque for the eclipse. I stayed at my sister's house, and as we were watching the eclipse progress, I had noticed through the leaves that you could see the shadows, and I remembered from one of the previous presentations, there was mention of that. So I went during total annularity, I went around and took a bunch of pictures, and this is actually in front of the house. They have a cement walkway that leads to the driveway, and I thought it was really pretty cool. So I just had to take a couple of snapshots of those, and I just sent one off to you.
I love it. There's a lot of wows in-house, so great job.
Thank you.
So yeah, keep those pictures coming. I love seeing all of those. I know we're going to get to having a little bit more next month. Also to note for anybody who's new or online that these meetings, the general meetings every single first Thursday of the month, are free and open to the public. You don't have to be a member to come and sit with us in-house and hear about our talks or join us online. Just show up, have a good time, maybe learn something. Maybe we'll get you hooked onto the hobby and become a member later, but feel free to just come and check us out. All right. Off to our current board before we start into next month. Here we go. There we are. So I am Trina Johnson. I am your current president for another year and 2 months before somebody else has to take over. So that's great. We've got Vice President John, who's in the house, along with Dave, our secretary. So welcome. We also have Matt, who is here. Oh, and just for the people here in house, this camera is showing this side, that camera is showing that side. So everybody at home gets to see you. So you can all wave and say hi. Although the people at home can't wave back to you, but it's okay. Conrad is online and Ahmed is off doing some family things tonight. So thank you everybody for being a part of the board. We appreciate you and love your participation in all of our events and running the MAS. Which leads me to the elections. Tonight, please, if you are so interested in being vice president, treasurer, or board member at large 2, which is taking over for Conrad, this is the last night for nominating either somebody else or yourself. It doesn't have to be, a thought about it. So let's see. So yeah, so tonight at 9 o'clock is your last chance to do that, but we hope that you consider it. So, and then next month in December, we are having our voting and presentations from all of the people that are volunteering for these positions. So come prepared with a little bit of a speech, either hopefully in person, if you can come, or online to just kind of talk about you and why everybody should vote for you. And then we will have a vote.
One thing on the top line there is December 2026. Really, 2025,
yeah, technically, yes. Well, yeah, it's January through January of there. So yes, we will get that corrected. So thank you. And your nominations just sent to board member 1 at mnastro.org. And so while at next month's meeting, while we are tallying everything, making sure we're having a quorum. So right now, I think we have 686 members. So we need 69 members to be here and voting online or in person. There will be a registration for the Zoom meeting so we can, at least for the ones at home, so we can verify that you are a member and that your vote does count. And it's one per family unless you choose to have husband, wife, or partner do your own membership, then you get to have two. So if there's any questions about that, let us know. While we are doing our voting, we would like you to send in your aurora and eclipse pictures. So we have something to watch as part of just a slideshow to take up some oohs and ahs while we are doing our counting and tallying before we get to saying who is going to be vice president and treasurer and board member too. So to send it to Ahmed. So thank you very much. And just a quick reminder about budgets before we get to the treasurer's report here in just a moment. Just send them on in, get them all done. If you have any questions about it, let us know. And now to my favorite part, I get to welcome the new members. I believe we have, what did I say, 10 new members? I think that's on there. Oh, I might have mistyped my notes on here, but thank you for everybody who has joined in the last month. We really do appreciate it, and or renewed. And is anybody in-house that is new that's recently joined? That's all right. Anybody at home, feel free to type a hi, I'm new in the chat, and we'll give you a hi welcome. And thank you for becoming a member and joining us in our little obsession here. So, but I do want to have a special little tidbit of a presentation for something that doesn't happen very often. I didn't prepare this, have decided as a board to honor Professor Larry Rudnick, if you want to come up here, with an honorary membership to the MAS. He has done quite a little bit for our club, so thank you very much, Larry. And here is his little certificate that says, yep, so honorary membership to Professor Larry Rudnick on November 2nd, 2023. So congratulations and thank you.
When I started talking to this group, I was 2 inches taller, 15 pounds lighter, and had a lot more hair, but I'm still glad to be here.
Excellent, excellent. Well, here's the rest of your, hey, Larry. I'm going to scooch back here. Here's the rest of your paperwork. So you get a card, you get a letter, and you get a whole welcome kit. So there we go. Oop. Happenings for November. Ooh, it's still a long list. There's a lot of things going on, even though it's going to get colder. So sorry, I'm not saying the other word. I'm just saying colder. So it's still valid to go out every now and then to get out there. I forgot to update the times for sunset and sunrise, but we do have a last quarter moon coming up. We do have a lot of moon conjunctions or close calls that are going through. We have our Taurid meteor shower. So hopefully people will be taking some pictures of some star trails and meteors that go through, and the Leonid meteor shower. So 2 in one particular month. I don't know how often that happens, but it's kind of cool. Every year. There you go. Thank you. I meant other than this. So, you know, more than just this one. So it's okay. I'm up here. I'm here for you guys. That's okay. In a year and a half, somebody else can try this one. It'll be good. And then we're back here on December 7th for our next meeting. So welcome, and feel free to come in person if you can. If it's not snowing, stay home. Be safe. So, oh, I said the bad word. So, yeah. Loaner Scope program. Antone is off. So John, do you want to take it? I think he's actually doing going to a lecture tonight. So.
Yes, for speaking for Antone and anyone who has participated in the Loaner Scope program, knows Antone. He runs the program very well, swapping out the scopes. For the new members, this is and even for those who have been around and aren't really familiar with it, this is an excellent opportunity to check out telescopes, different types of telescopes before you purchase. We have 18 telescopes and binoculars of multiple varieties. The most popular, the C8 and the 8-inch Dob. The C8 is computerized. The Dob is not. The Dob is probably recommended for beginners, but you can see what the difference is once you start using these. We also have a solar scope that you can view the sun, and it's an H alpha. So it gives us some really nice images, and we have binoculars. It's a wide variety. Check out the website and the Loaner Scope program, and also available are presentations. These are DVDs. They're very good programs, and you check them out. And just like the Loaner Scope program, you can have them for 30 days. And you can have it longer than that for another 30 days if no one else has their name in the pool wishing to take one. So keep that in mind and make use of this. It's available to all members.
Yep. And I've checked out a few of them, and it comes with the DVDs. So you can listen to it in the background if you want to. Otherwise, there's also a book that comes along with it. So if you'd rather read about everything that they talk about in the DVD program, you can also read about that too, and kind of take it with you and kind of go back and forth through that. So thank you. Thank you, now. Upcoming star parties. I believe ELO is having their last one this Saturday. All right. And then it'll get kind of cozied up for the winter, and that's true. That's true.
There is an additional LLC.
LLCC weekend, November 10th. So if you're interested, and sign up on the forum to get a room. We'll keep a track on the weather, whether that's going to be open or not. But
Okay.
we added one more weekend.
Oh, awesome. Awesome. So last chance to go up to LLC November 10th. So perfect. And of course, CGO, we're going to keep it plowing through the winter. So if you wanted to go down to CGO, you can certainly go out there but take a little snow shovel with, because the pathways may not be, shoveled, but the driveway should. So, and if you have issues down there, just let us know so we can get that taken care of. And of course, the annular eclipse is done, so I don't have that countdown up there anymore. I have the total solar eclipse, which is 160 days away. So hopefully everybody is getting prepared and getting set and practicing all of your stuff. I'm going to just step away from that one for the practice. Thanks, Scotty. Yep. If you have a badge or ordered a badge, Chris is here, but he also brought the badge cloak with. So if you have one, take one home, or the paperwork's in the back of the room to sign up and get one made for you, along with a couple of free items back there as well. And of course, Mark has asked me to talk about Globe at Night, which is always a good thing. I don't have a spiel this time. I think we've kind of covered it in the last few months, other than going out there doing globeatnight.org, take your readings, seeing what you can see in the night sky and post them onto their website. So it keeps us, going through and keeping our lights down, and hopefully they will get enough data and make a difference, which is always the good thing, because we want to preserve our night. Astronomical League. Usually Jerry is here. He's kind of leaving that up to me for a little while, but I do have a couple of awards that came through from him. And for those that don't know what the Astronomical League does, they are our parent organization, which gives us observation lists and trajectories and focus in order to take the next step in our learning process, if you so need it. I think it's kind of fun because you also get these cool little pins and certificates that say, hey, you have achieved all of this. So we have two of them tonight, and I'll start with Mr. John Simage for doing the honorary Messier. I don't have the certificates. I think they were mailed to you guys. So well, you can come up and talk to these guys. There's the thing. Honorary. I thought the Messier did that. Unless you did it separately.
No, the honorary is the main. There's like a mini version that you don't get a pin.
No.
If you want the pin,
Do
it's
that one.
called honorary. I know I was confused when I did the program and I thought honorary, what do? You just have to act smart and then you get one.
Well, it's not like Larry's
Yeah,
honorary.
like Larry,
He got
you
a
know, that-
certificate.
You get
so-
honorary stuff when you're smart like that.
Yeah.
No, and I don't qualify for that. So, no, the honorary Messier is you have to look at all the Messier objects. And this is what I always viewed this one as the benchmark. And I've been doing astronomy seriously since about 1972. So it took a while for me to get this one. No. No, yeah. So it's not that difficult. Okay.
One a year.
No,
That's a good one,
the reason being I hadn't been in the MAS until I moved back here. I moved away. I did it. But I've seen all these objects before, but I never once logged anything. Never. For, like 50 years of observing, I didn't write one note on anything. So the only thing I did record, is if I took pictures of something. But so when I joined the MAS and then I started doing astronomical league programs in 2018. So that's and what's like I say, this is the benchmark. It's that list I've checked off the list. I have check marks next to all these objects that don't qualify for anything other than, just personal. I saw this, but this one here was really fun and it brought me back sort of when I was going through this. And you also, Messier objects are everywhere. So it takes you a while to get it because they're all over the place. And being up here in Minnesota, there's some that are in the south. And the last one, M79 in Lepus. And I had that one left going into at the last year. We had really crap weather, probably the worst observing weather, I think, in the past year. Maybe just start a few months ago and then back that I've ever had in my life. Okay, and spring or fall comes and Orion is setting in the west and M79 and I see all the stars around it, but I don't see it. That's a test of character when you have that one last one to get the award and you're going, do I see it or don't I see it? Oh, I think I see it. And it's like, no, you don't see it. And you just, okay, spring. And so spring comes and, that now actually that was going into spring when it was setting out there. And so I just had to wait. And what I waited for was the annular eclipse because I was in New Mexico, and guess what? Orion and Lepus are really nice and high in Mexico, but I had to get up at 4 a.m. I had my scope set up at night. I covered it up. I got up at 4 a.m. I ran out. I pointed it. When I was in Bortle 1.5 skies where we were staying up in the mountains there. But so I could almost see it. I think that's it. And I pointed the scope at it and sure enough, that was it. So I could see it with my naked eye down there, but yeah, and then it's okay, I got the award. So yeah, it's an adventure sometimes, these programs, but I really encourage you to do them. And this is a good one.
Congratulations. So thank you. I don't know. I completed my goal for the Messier, all of it was 1 year and I actually did it. So you don't have to take 50 years to do something. And then of course we have Dave Tostison, which is the Universe Sampler Award for Visual, Binocular, and Telescopic. I don't know, I'm not sure. Does anybody know about it? They can talk about it. All right. Well, anyway, he has completed that. So congratulations to him, and hopefully we'll maybe have him, show up next time with the pin and we can see what that looks like. I'm all about the pins. I like the bling. And it's,
So all together now, get out.
all right, 1, 2, 3.
Get
out there
there
and
and
observe.
observe.
There we go. Thank you. I like that, Matt. And I know everybody went to the annular eclipse. Okay, not everybody, but a lot of you did. So please submit your articles to the Gemini so that way Father Brown has some, or anything else, and you know, the whole adventure, whether it was good, bad, or terrific or ugly. So and then anything that you've learned along the way. Father Brown has, it's the articles that you guys write are so cool, and I just love reading them. So don't think everything is important, so write about it, please. And then we have our happenings. So if we have something that is coming up or you need help or something, talk to Dave and we'll get them into the happenings. What are you doing?
Sorry. Trying to fix stuff.
Big stuff. Okay. Well, that's about all that I have for tonight. Yeah. Hold on. Yes.
I posted this on the forum. A few of us, weather permitting, a few of us are going to go to the Goodsill Observatory tomorrow night. It's on the Carleton campus. They have an open house once a month on the first Friday. They have a 16.2-inch refractor. I think it's a Brashear refractor from about 1886 that they still use. It's still in good shape, but they still use it. They also have an 8-inch Alvin Clark in a separate dome that they show objects for people during their open house. I went a few years ago, and it's a really neat place. It's close to 50 miles south of Minneapolis, but it starts at 7:30, so there should be enough time for people to get there after work or what have you. Again, it's weather permitting. If you're interested in coming, see me after so we can just coordinate. We're planning to meet up there about 7:15, and again, it starts at 7:30. So.
Okay. Did you post that on the forum or no? Oh, you did. Okay. All right. All right. Perfect. And it's in the happening. So information is getting out to you. Perfect. All right. So I have the first of our wonderful speakers tonight. If Allan could come up here and I can get my screen to work, and he has giving us kind of like a part 2 to his planets.
Yeah, this was a continuation of last month. I went and talked about planets, including a dwarf planet, and kind of issued a challenge to go image Eris, the dwarf planet, which is more massive than Pluto. And I think that I actually managed to do it. So on the left is a Sky Safari image and some Gaia stars labeled. And instead of putting that big Gaia label, I labeled them little star A, B, C. Then there's D, E, F, G, and then H on the other side, and where Eris is supposed to be. And so I figured, you know, with Eris being 18.6 magnitude, I need to go get my 14-inch C14 out there. So I dragged out the 50-pound tripod and set it up on the pad at Cherry Grove. And I dragged out the 50-pound CGXL mount, and I couldn't get the mount all the way down on the tripod. It was like stuck, and I couldn't rotate it, and I couldn't get it off either. So now I'm there with the car over in the parking lot and 100 pounds of integrated hardware on the pad. But I managed to get all that back in the car. It separated the next day. There was a little sticky label that was from the scope that had gotten on the bottom of the mount, and that sticky label jammed between the tripod and the mount. There's just not enough clearance. So I went and scanned and found the rest of the little pieces of sticky label that had apparently gotten in there. And anyway, so I ended up using my 81 millimeter scope to try and image an 18.6 Eris. And I think it's in here. There's a little spot right there that looks like it's about the right place with the stars there. So I think I managed to capture it there, but it's questionable. And I had to go out the next night. And the next night I was able to use the 14-inch. And so Eris obviously had moved by the next night. So I said, okay, I need to look for it having moved. And so I have little stars A, B, C, D, E, F, G again, H. And then there's 3 little stars in here, one of which should be Eris. But how do I know which one's Eris and what's not and what's an artifact and and what's, problem due to the poor guiding I was having and stuff like that. So then I went and got a digitized sky survey image of this region. And the key to this is use star HD 10997 to get in the ballpark, because that's something that all the catalogs happen to have. Because if you don't find that HD star, most of the catalogs, you don't know anything about Gaia. Some programs know about Gaia, others know about type, but anyway. HD 10997, there's the key. And so the DSS image is on the left there, and I can see the two little stars right about where they are in the image I took. Eris is there, it's brighter than the two little stars. It's not in the DSS image. And I can find some other things in my image that are a little bit deeper than the DSS image. So I actually think that that little dot of light that's smeared out there is actually Eris. So anyway, that's my closing adventure to the planets of last month, where I actually think I found Eris after much heft of 100-pound objects.
Cool. Thank you. I believe them. If anybody disagrees, I would love to see this and your images to compare to this. So we'll come back to this.
Is this going up for peer review? Is that what we're doing here?
Yeah, why not, right? Allan, you're up for that, right? Yeah, okay, yeah. Why not? All right, so next month, December 7th is our next meeting. And just a little note about the board elections and the member Aurora and eclipse photos. Dave, did you want to talk a little bit about the Aurora Summit at all?
Well,
Just to kind of get a pre-Aurora taste for next month's pictures?
So tomorrow, I'm leaving and going up to the Red Cliff Indian Casino reservation, but it's up just north of Bayfield, Wisconsin, and it's actually a little casino. They don't light up like the big casinos, and it's for the Aurora Summit. And this is a group that gets together. It's really primarily photographers and people who go out and observe the aurora. They're not astronomers per se, although there's certainly some astronomers in the group. And they held it. Usually, it's the first weekend in November every year, and it's a great group to get together. They have a lot of great speakers. Bob King will be speaking. Mike
Shaw.
Mike Shaw will be speaking. In fact, he's one of the organizers of it. And weather permitting, Friday night's supposed to be clear, so we might. It's right on the southern shores of Lake Superior, so we have really nice view to the north, and so we might see aurora. In past years, it's been kind of hit or miss with clouds. So, but it's a great event. I don't know if there's any more openings for this year, but you may want to mark it in your calendar. It's a fun event to go to, and they're great people.
I think on Facebook, Dixie marked it as registrations were closed.
Okay.
Like about 2 hours ago. So, yeah. All right. Thank you, Dave. Much appreciated that. One of these days I will get there. So. All right. So at this time, I would love for Larry Rudnick or Professor Larry Rudnick to come on up here and talk to us about the odd radio circles and odder radio cubes. So welcome, Larry.
So first I wanted to note it really is an honor to be honored to be an honorary member of the society. I have worked with the society for many, many years, and it's always been a delight, but I do have to ask the question of, do you really know who you're bringing into the club? And so this is me in graduate school. So this picture is probably from around 1970 or so. Does anybody recognize the guy below me? Anybody know? He's associated with the picture that's spinning around. That's Dave Wilkinson, and that's the W map sphere. And Dave was my thesis advisor, and wonderful guy. And he sent me down for a summer to work at Green Bank for, I feel like I'm echoing too much. Can we just turn down a little bit? sent me down to work with the engineers there just so we could learn something about radio astronomy, instrumentation and stuff. And he had a wonderful idea at one point. And for those of you familiar with it, the intergalactic medium this is in the early 70s, we weren't sure there was anything between the galaxies. So we knew the galaxies were filled with stars and dust and gas and stuff like that. Some of it was hot, some of it was cold. We didn't know if there was really anything. There were hints from X-rays and stuff. And he came up with the idea that if there were sources of radio radiation that had very fast timescales that emitted pulses, that there's this thing called dispersion measure. The time of arrival of the pulse is different at different frequencies due to the plasma that it's traveling through. So if it was traveling through a plasma, we would see a dispersion if you compared a pulse coming in at one frequency compared to another. So he gave me this idea and said, why don't you, do something with it? And so I built a receiving system, and on the roof of the physics building in Princeton, I built a helical antenna with a giant ground screen and stuff like that, and was looking for, didn't find anything, but was looking for what are today called fast radio bursts. I mean, these things actually do happen, and they are dispersed, and you can actually measure the intergalactic medium. So his idea was right. It was just, we really weren't set up for it. But there were a lot of signals that were coming in through this antenna. So you could look on the oscilloscope and you could just see all stuff coming in. And one of the things that I had learned down at the radio observatory is if you don't know what it is, what signals you have, take the thing and don't run it into a computer or digitize it or a chart recorder or anything. Just put a speaker on there and see what you can hear. So I put a speaker on there, and sure enough, I'm picking up ham radio operators. That was at reasonably low frequencies, and one guy just came booming in. So this is in the days before the internet, of course. So I had to go get a membership directory. I mean, I had his call sign. I had to go get a membership directory. This story really is going somewhere, you'll see. But since you let me start early, I figured just go for it. I have time. Okay, so I had to get a directory. I got a directory and looked the guy up. And it turned out that he was about 20 miles down the road from Princeton, and he was doing moon bounce. So he had a dish in his backyard. I can't remember, it was at least 15 feet, and it might have been 30, but at least 15. And he was bouncing signals off the moon and then talking to people anyplace else on the earth. It's something that the ham radio operators do. So I told him why I had contacted him, that I picked him up on my astronomical radio telescope, and he invited me to come out and see his rig. So I went out there and saw this big telescope, which was surplus from Bell Labs that he had gotten, and he had it running in his backyard. And he had a little sighting scope on it, so he could just point to the moon. I mean, he was bouncing off the moon. He could just look and line the thing up with the moon. I don't remember how he was tracking, but it probably could just keep doing it by hand. But he might have had a drive on there and stuff. And so what he wanted to do, so this is something like what it looked. This is not his, but it is a ham radio operator's moon bounce telescope that I just happened to find on the web, and it just gives you a sense. The surface is not solid; it's just a mesh. You don't need the wave, as long as the wavelengths are longer than the openings, you're fine. So he wanted me to come because he thought, well, we could point at some astronomical objects. You know, he's doing this moon bounce, but I'm an astronomer. I can show him some things in the sky. We'd be able to point the telescope and see the signals coming in. So I took with me the book Radio Astronomy by John Krause from Ohio State, because in the back of that was a list of all the strongest radio sources in the sky. Last couple pages, strongest radio sources in the sky, and there are in deck. And I figured that's it. I'll come there and we'll find who's up and we'll point out and see if we can detect those things. But then we ran into a little problem because I didn't know what LST was. I didn't know what you were supposed to do with the RA and DEC. And we were just kind of floundering there and stuff. And he asked me, well, how is it that you observe? And the answer is, well, you use these things. What you do is you go to the telescope operator with the coordinates punched in on the card, and you hand it to the operator, and he makes sure the telescope points where it's supposed to point. So now, having heard this story, I ask you again, is this a real astronomer, and is it really okay for me to be a member of this august group? Yeah, right. Get out there and observe. Okay, so at any rate, thank you again. I'm delighted to be in this way a part of the group. I have two different topics to talk to you about tonight. I spoke to this group last in June of 2022 and showed you all kinds of crazy things that were coming in from the precursor telescopes to the square kilometer array. And I'm going to do a follow-up on a couple of those topics that have turned out to be, really interesting and stuff. So to set the stage for the odd radio circles part, I wanted to talk about unexpected discoveries in astronomy. And I didn't make this list up, I just looked it up on the web. And the list is extremely impressive. The expansion of the universe was not expected. It was a result of doing the observations, of getting these redshifts and finding out that they correlated with distance and discovering the expansion of the universe. It wasn't science like make a hypothesis, go out and test it and stuff. Most of astronomy is exploratory. And when you look at the big discoveries, almost all of them were serendipitous. The cosmic microwave background, complete accident. Penzias and Wilson at Bell Labs having extra noise in their telescopes, and connecting up with the Princeton group that I was part of a little bit after this discovery time. Radio galaxies, completely fortuitous, pulsars, gamma ray bursts, dark matter, dark energy. The list just goes on and on. These are not things that we predicted in general. They are things that were unexpected, and then you have to be open for them. And so Ray Norris, who I stole a number of slides from, astronomer in Australia, was driving force behind one of the major surveys with the Australia SKA precursor, put together this list of discoveries that have been made with HST. And it's an interesting list. In the top, in that orange box, are what we call key science projects. So those are projects that were decided on ahead of time, where the community got together and said, what do we all agree are such important projects that we're going to not wait for people to propose them and stuff. We're just going to define them as a key project. We're going to give them lots of time on the telescope. There'll be teams, they'll be organized, there'll be procedures for how you share data and what people do, major efforts in the key science projects. So that's that first list of three. And then the list under it with the check marks here, it says planned. These were things that individual astronomers and individual groups, they hadn't gotten to key science project level, but they were important enough that they had programs that went on HST. And now if you make another list, and that's where this list is actually generated, and that was National Geographic did a top 10 hits of Hubble. And the question is, where did the top 10 hits of Hubble come from? And the answer is one of them came from a key science project. That's Cepheids doing the distance scale, measuring H0. Whoops. Uh-oh. Yep. Oh, thank you. The planned observations ended up being good. They got the mentions, but that bottom list, the other half, of the top 10 were things that nobody had planned. That was the serendipitous stuff. So it gets to the top 10 list. And the answer is, if you're going to come out with a new telescope and stuff, you better be open to the things that you're not expecting to see, because they're going to end up being in your top 10. So there's two of these telescopes, two precursor arrays, one in South Africa and one in Australia, that were developing some of the technologies that are going into the square kilometer array, which right now is in early construction. And I'm involved with projects on both of these. And one of the outcomes of this, Ray Norris, who I mentioned, was really interested in keeping his eyes open, making sure that the processing that we were doing and the way we were looking at the data left us open to see things that we didn't expect. And it's very tempting, especially when you're overwhelmed with data, to put a very fine filter on it and just say, this is what I'm looking for. And then you go and you look for it. And if you do that, then you miss out on these other opportunities. So he was very strong in saying we need to keep our eyes open for things that we don't expect. And in fact, he found, and then other people chimed in and stuff like that, found these things which he dubbed odd radio circles. And I've been involved with a number of the projects trying to figure out what these things are. So you take a radio picture of the sky, about 1 arc minute across, you see a circle, and that's where you see pictures of the first 3. I'll qualify that in a second, of rings of radio emission. So the dark is just a ring of radio emission, about 1 arc minute across, very faint, very rare, but there they were. And we do have other circular things that we knew about. We know about supernova remnants, which show up in the radio. So these were not supernova remnants. There were various ways that could be ruled out. Not planetary nebula, because they can sometimes show up as circular. Not a spiral galaxy seen face on, because in the radio, if you get a nice spiral galaxy face on, often you'll just have a ring of emission. So it wasn't any of those. It was things for which we couldn't figure out what it was that was causing it. So a ring about 1 arc minute in diameter with no known obvious cause. And then we had an honorary, so these are ORCs, odd radio circles, ORCs. And then we made an honorary ORC from this one, this little faint smudge of emission that I want you to pay attention to there. It wasn't a ring, but it was kind of circular. It'll look like a disc of emission, barely above the noise. You can just barely kind of see it there. And because it was sitting next to this other ORC2, we decided to call it ORC3. So there's more and more of these happening. We're finding them all the time now. And so this is just sort of a little menagerie of some of them. And I'll say a few words about some more of these later on. Some of them, we could figure out who the host was. So the host is the word that we use in radio astronomy to talk about what was the source of the emission, either in the optical galaxy or often an infrared galaxy. How, you know, that's the thing that hosts the supermassive black hole in the case of radio galaxies that presumably is the source of the emission. And so the question is, did these odd radio circles have hosts? And the answer was some of them did. Sometimes there was actually a radio core in the center, and you can see that in these two. On this one, it's not quite as clear, but if you look in the optical, there's a bright elliptical galaxy sitting right in the center of these things. And you can calculate what are the chances of just finding a nice bright elliptical right in the center of one of these circles. Chances are really tiny. So it is quite likely that these bright elliptical galaxies were the hosts. Give you a sense of how rare they are, though, 1 every 50 or 100 square degrees. That's it. So you could estimate now what the total number of them which will ever be discovered are, at least the ones that look like this. I'm not going to try to do that calculation, but one could do it. So we have at least some of these that are probably associated with something that happened in these elliptical galaxies. But we've never seen a circle around elliptical galaxies before, so we don't know, what's going on. We started sort of looking for clues. So one thing you can do is you can look in the environment. You can ask what else is going on around them. So you try to find other galaxies at the same redshift, and sure enough, they tended to be in places where there were other galaxies at similar distances. So we would say they were in overdense environments. And that's not all that unusual. Most galaxies are somewhat in concentrations. They're not randomly, uniformly spread. They're in these beautiful clumps and clusters and filaments and things like that. So this really didn't, it didn't really add all that much information, but yes, they were sort of typically like other galaxies and concentrated with them. So one of the things that we needed to do is to get better data, get better pictures of these. I mean, the pictures were low signal to noise, not very high resolution. And so for ORC-1, the one that I was showing you before, we went to the Meerkat telescope and got the image that's on the left. And I know how to make those kind of images now. It's a real skill of getting the right kind of color schemes and doing these overlays. You get this kind of ethereal type thing. So, and I'll show you one of those actually at the end. So this is ORC-1, and it's more complicated than we thought. It's not just a simple circle. In fact, it's at least two circles and maybe some other structures as well. There is a core, so right in there is a little radio core, and sitting, since this is overlaid on the optical image, sitting on top of one of these elliptical galaxies. And so now we've got a more complicated structure that we need to explain. And some of the work that I did was looking in more detail at different aspects of the radiation that were coming. So what we call on the radio spectral index, which is just the colors of the galaxy. So what are, of the radio emission, what are the effective colors? What's the ratio that you get when you look at it at different frequencies? And that turns out to be connected with the physics of how those particles got accelerated. This is all synchrotron radiation, by the way. And you guys can interrupt me. I know that, I have professor in front of my name, but you can interrupt me and ask questions, because I never said that we were looking at synchrotron radiation, and we're looking at synchrotron radiation. So the synchrotron radiation, if you look at the spectrum and measure the colors, basically the ratio of high frequency to low frequency emission, that's connected with the physics of how relativistic electrons, which generate the synchrotron radiation, how they got accelerated. That's one of our big themes, is if we see synchrotron radiation, it means that some electrons have been accelerated up to almost the speed of light. And when they're in the presence of a magnetic field and traveling at almost the speed of light, they give off the synchrotron radiation. And the question is, who accelerated? What did that? How did it happen? And that's one of the questions that motivates a lot of the work. So you measure the colors, you measure the spectral index, and you try to find out, can you figure out where they got accelerated, how long ago they got accelerated. So the answer was no, it didn't give us enough information. That's the first look at it. It wasn't of great diagnostic value. The other thing we looked at was the polarization. So synchrotron radiation is polarized, and you can, from that polarization, figure out how ordered the magnetic fields are. So there's magnetic fields in them. They can be nice and ordered, or they can be chaotic. If they're nice and ordered, then you get a nice big fractional polarization. And these had strong fractional polarization. And here's a picture of the fractional polarization, and it's strongest around the outer edges. And then here's a picture of the magnetic field lines, and they're wrapping around the circle. That was the first thing. Okay, here, can you see the mouse now? Oh, I've been moving the mouse the whole time and you didn't.
Up on that screen.
Yeah. Oh, should I start over? What? Yeah, no, I can,
Yeah.
I'll be able.
Okay.
Oh, turn it. Okay,
So the,
if
yeah.
I, if,
Here.
okay. I don't know why it's there. Whoops,
They're on or off?
it's on. Yeah.
There we go.
Okay. Can't believe you guys let me go that long. I was having a good time with my mouse. You don't know all the things I was trying to show you. Yeah.
Better if you just point at the screen.
Well, I don't know if that works on Zoom. Zoom's not looking at that screen.
I have a camera.
Oh, okay, go ahead.
So, bring that, perpendicular to each other.
Well, if you take two overlapping circles like that, then where they cross, it's going to look perpendicular. Yeah, so when the circles cross each other, then one's going sideways while the other's going down. So I kind of see two circles there, one of them kind of smashed a little bit, but other people have drawn other shapes in there. And in fact, the next half of the talk, I'm going to be talking about 3D geometries, because that's really the key. We're looking at this in 2D and we're trying to figure out in 3D, what does it really, look like? So what I was mentioning is over here, we're now looking at the fractional polarization, and it's strongest around the outside. So that means that the fields, the magnetic fields, are more ordered on that outer edge than they are in the interior. And they're lined up, wrapping themselves around the circumference. And this was great because we've seen that before. We've seen those patterns.
I had one comment online, and I had the same thought, is it kind of looks like a planetary nebula.
It does. Yeah. I'm sure you could get ringers for, each of these, find who's the closest planetary nebula, to each of these. And this definitely does look like that. So for supernova remnants, if you've got a ring of emission, the fractional polarization is highest on the outside, and it depends what stage of life it's in, the magnetic field will be wrapped around the outside. And we know where they come from. They come from explosions. So this was the first clue that maybe we're looking at an explosion. We've never seen that before from an elliptical galaxy. That's an enormous explosion. And instead of making one of these nice long radio galaxies with jets and stuff, which is what most things look like, and I've shown you here before, some of these actually had spherical explosions or bipolar explosions, maybe, to make the two rings. So a good hint to start out. But then there's people that, so this was one of the ideas, and we worked out numbers and stuff, and it's enormous. So it's the numbers, for those of you that think in ergs, and I really don't expect anybody will, the supernova has about 10 to the 51 ergs, which is about the same amount of energy that the sun puts out over its entire lifetime. So it's something like that. That's what comes out in a supernova explosion. And these objects, the energy involved was somewhere between 10,000 and a million or 10 million even times the supernova. So it's not like a supernova explosion. It's tens of thousands or hundreds of thousands of times more energetic. But that's the kind of energy that you can get out of a supermassive black hole. We had seen this before in radio galaxies and stuff. That's this amount of energy coming out. And then this is just a fun one that I had worked on a little bit, and I included here because it's a bit of a fun story, where it looks like there's kind of quadrilateral structure. There's a ring, but then looks like maybe two jets came out in two different directions and made these hot spots and stuff. Somebody else had studied a similar object now we're looking at, in the image I'm showing you here, X-rays, where there are holes that have been carved out by the explosions that probably jets that had shot out in that direction and evacuated cavities. They interpreted that as what happened in the merger of two supermassive black holes. And that's kind of fun because that's what the gravitational wave people are going to be looking for now. And in fact, we have some evidence from the ripples of that have now been seen in the background for gravitational waves, that these supermassive black holes, 1 billion times the mass of the sun, if two galaxies, each of which has one, merge, they're going to give off enormous amounts of energy. You can create an explosion, you might get jets. So that was fun. But the reason this subject was really fun is that in the survey in Australia that I'm showing you some stuff from, when it's complete, and we're about 10% complete now, there will be 40 million objects. So that's how many objects will be in this, radio objects will be in the survey. And the question is, who's going to look at those? I don't care how many awards you give out. It's like 40 million, we're not going to do it. So there's people that are doing all kinds of clever things to try to figure out, how do we sift through? Oops. Oh. Okay. How do we sift through all these pictures? Michelle Lochner, a young astronomer in South Africa, developed a machine learning technique to take images. So you just feed it a whole bunch of images, thousands of images of objects, and without telling it exactly, she guides it a little bit, but really without telling it what to look for, it finds the ones that don't fit. So, and she calls it astronomy. So looking for anomalies in astronomy. And it's amazing. It knows the difference between, if I have a nice double structure with jets, it knows that it's seen that before, even if there's a big one and a small one, rotated a different angle, one thing brighter than the other, fat, thin. It goes, no, those are all similar to each other in many different ways. But she finds the ones that don't fit. And I went through a process on the Meerkat telescope of having people send me all kinds of suggestions for interesting objects, and long process of winnowing down from thousands of objects to about 100 suggestions that were sent to me picking out like 7 or 8 of them to put into a paper because they really were interesting enough. Michelle found half of them by her computer program. It's like, oh my God, it's a good thing I'm retired now. So, okay. So that's going to be part of the wave of the future, is these machine learning algorithms. So people are asking, well, is there any alternative to the explosion for getting a nice spherical ring-like structure? And so there's a couple of other models. One model is that there was a period of active star formation with thousands and tens of thousands of supernovae going off. And the cumulative energy from all those drives a kind of a blast wave, like a shock wave, out into the medium. So that's another idea that's on the table. Details don't work out all that well, but it's still kind of a possibility. And then, whoops, I lost a slide. That's okay. At any rate, so we don't know yet what causes those. But what we do know is that there's more than one kind. That these circles that we were finding, the ones I've just been telling you about with these ellipticals at the center, there's another group of them that don't have ellipticals at the center. And these are pictures of 2 radio galaxies. So host in the center, jets of emission coming out, and then all kinds of interesting things going on in the lobes. And one of the ideas was that if you turn one of these things and look at it end on, you might see something that's kind of circular. So that was another idea that people were putting on the table. It wouldn't happen very often, but it doesn't need to happen very often because there's only one of these every 50 or 100 square degrees. And then we started finding that there were circles in these radio structures that you didn't even have to be able to look at. You didn't even have to be looking at it in the end. So here's a jet coming out. The optical galaxy is here. Whoops, I didn't mean that to go, but that's okay. You can enjoy that, and I'll tell you about it in a minute. And there's a ring of emission, probably seen at an angle, so it looks kind of elliptical. But if we looked at that end on, it would be a ring. And then here's another kind of strange ring. Whoops, thank you. Here's another strange ring in a radio galaxy. So this is Chris Nolting, who got his PhD from Minnesota 5 or 6 years ago now. And one of the things that he does is he does computer simulations of jets of radio emission that are precessing. Oh, this is as bad as patting your head and doing, whatever. You're doing that thing where they're rotating around. That will happen if there's some kind of torque, which you can have if you have a binary black hole or you have a disk of emission around the black hole that's tilted. The jets will end up processing around like the Earth processes on its axis. And what Chris said was, if you look at one of his things end on, and we'll see if we can get this to light up again. There we go. And then you wait, so you can, we're looking at it end on now, and you can see the jets, and then the jets finally turn off right there. And for a while, there's a circle of emission there. Don't know. Maybe that's one of the things. We don't know if we found all the kinds of these arcs. We now have to start naming them, which I didn't appreciate, but really is a critical thing in astronomy as an observational science. What are you going to call them? Because that sort of starts putting interpretation on what you're seeing. So we could follow strong astronomical tradition and call them type 1 and type 2, but that's kind of useless, and hopefully we won't end up doing that. Okay, let's go on here. Oh, this was the last one that I was looking for. Shock waves that are generated when matter falls into a galaxy. So we know that clusters of galaxies are still forming at the current epoch. Materials falling in onto these clusters and they're growing. And when you fall into an individual galaxy, you could set off shock waves. So there's a group in Germany which has suggested that. Am I in the wrong place? Yeah, go ahead.
5 or 0.5 megaparsec. What is that?
0.5 P. Where are we? Which picture?
On the left.
The image on the left.
No, 5.
Oh, I don't know. Well, I didn't make that label. I'm going to have to write to the. Say it again. That's great. I never even noticed that. The true scale is about 5 megaparsecs. So my guess is it's just a typo. Yeah. That's great though. I'll write to them though.
Well, those are just like the ones that Dr. Carl Brett studied.
Mm-hmm. And a lot of people study them because we're looking at how filaments and clusters forms and looking at large scale structure. And that's what I'm showing here, except that when you get down to the individual galaxy level, and if you look at, whoops, just watch this movie and you will see little places where sort of spherical shells come out. So when something falls in and dumps a lot of energy, you get these little spherical shells expanding, and that's what the group, and there's one that just went off. That's the suggestion that this group in Germany is making. So we don't know yet. There's a lot to learn. It's fun. We did not expect to find these things. We had one mystery here that we found one of these circular objects, which we didn't think could be a supernova remnant, although it looked like one. And here's the Large Magellanic Cloud, but it was sitting too far out. So Large Magellanic Cloud's only a few kiloparsecs across. This thing was sitting twice as far out as the rest of the stars and stuff. But in fact, it turned out that, yes, it was a supernova remnant. So once in a while, we're going to get fooled. If you look in the X-rays, that's what's here. It's an X-ray picture, and that's a dead giveaway because the supernova remnants often have X-ray shells. So the redshifts are about 0.2 to 0.5. So we're talking about a few billion light years on that order. Yeah, pretty far away. And
Well, I mean, what was, if you were watching the Big Bang happen?
Mhm. No, it's an interesting question, but that's a kind of exotic explanation that people might put in the back of their minds and wait until nothing else pans out and then ask, is it something else that is seeded a mini Big Bang kind of thing? I don't think we're there yet because we have more plausible ways. We don't really know. Yeah, that kind of thing. But people don't do it out loud because it's a little too out of the box. Okay. Yeah. Mm-hmm. It could be, if you look at the distribution, take these nice deep photographs, you see there are stars that belong to the Large Magellanic Cloud that aren't part of this concentration, whether they've been pulled out tidally or they're just in the process even of coming back in. In the time that this supernova probably went off, I forget, we made some estimates, 20,000 years ago or something like that. You don't need much of a velocity kick to get out that far. So it could have actually occurred in the main body of the LMC, maybe in a binary system, gotten a bit of a kick and out there, because we do know about these very fast runaway stars that we can see in places as well. Okay, where am I? Okay, so now back to this question of the second type, the ones where there are rings that are inside radio galaxy lobes. If you remember that first object where I said this is the thing that I called ORC3, that was just this sort of very diffuse shell, and this is now a deeper image of that. And what's really clear to us that have studied radio galaxies for a long time is that the host was here. We used to think this was just disconnected radiation. We didn't think it had anything to do with the source. Now we are saying the host is here. It sends out a jet in this direction. A jet in this direction makes these two giant lobes which have been bent, and we see bent sources all the time, and one of them has a ring in it. We still don't know why. We don't know why once in a while you'll end up with a ring, but we're finding more and more of them. So here's another one with this is a normal looking radio galaxy with some bending, probably due to some winds that are coming by, and one of the lobes has a ring in it. So there's more than one way to make these odd radio circles, and we're going to need models to try to look more closely at what all the possibilities are. Here's two more where the radio galaxy is just one-sided. We're missing completely what was on the other side, but then there's these nice rings sitting right near a jet. So that can't be coincidence. You have a jet pointing to this ring-type structure sitting in a big cloud of radio-emitting plasma. So fun and games. I mean, it's not sorted out yet. What do we need to do? We need to find more of them, as many as we can. So Ray, who I talked about earlier, set up the Even Messier catalog. We were talking about the Messier catalog. This is the Even Messier catalog. And it's just a Google Doc where people can, when they find something that they think may be a candidate for one of these, they'll stick it on the page with some commentary and stuff like that. And we've got more than 70 or so of them now. Some of them will end up not being right. Some of them will be, other things. And we're not going to call them type 1 and type 2, but I don't know what we're going to call them yet. And there's just a lot of different disagreement about it. We need to get spectroscopy of the host galaxies to see if there's evidence for a lot of star formation that might have gone on, see if there's evidence for a supermassive black hole in the center from hot gas circulating around the center. We need numerical simulations that are going to be done. And there are other people. So I mentioned the work by Michelle Lochner trying to find unusual things. There are several different groups that are doing the same kind of thing and finding all kinds of odd objects. Some of them are these orcs, and some of them are other types of things. So here's a collection now of odd objects found. And this was just so cool that I had to show you why. They take a radio image, make a JPEG image or GIF image or PNG image of it or something like that. And then they compress it. And once you compress it, the size goes down. That's why you compress a file, so the size goes down. If there's a lot of unusual stuff there, the size doesn't go down very far. You can't compress it very much. So what they do is they look for the objects that won't compress. They just look at the gzip size. They look at the size of the file and say, look, if this were just a sphere, the compression routine would have figured out and just compressed it down to near nothing. But if it's a complicated structure, then gzip isn't going to do a very good job. And so they've been able to find all kinds of the most complicated objects simply by looking at the size of the gzip file. What's that? Why is it my name?
The name.
Oh, we call them gzips? What?
Ultra complicated objects.
Ultra, yeah. Except that there's some ultra complicated that aren't circular. So now we need to distinguish between the circular ones. Circular extra complicated objects. Okay. So yeah, look, my email is larry@umn.edu. You can just send me these suggestions. That'll be fine. Okay. So I'm having trouble reading the clock in the back. What time? I'm really good. As long as the audience isn't falling asleep, I'm great. So here's the second topic, which won't really take as long as the first. This is really disconnected. So just cleanse your brains, like take, whatever, take a little brain, whatever. Finding the 3D structures of objects is one of the key things we face all the time as we try to physically interpret what it is that we're looking at. And often we will have a mental image in our head when we look at these pictures of what the 3D is, even without thinking about it. It could be right, it could be wrong. When I was teaching, I did one exercise with students that was absolutely fascinating. And that is, I've been showing them all these pictures, and then in a lab, I gave them a bunch of modeling clay. And I said, make the structure that looks like the pictures that you were taking. And they couldn't do it. They did not have, and then I go, oh my God, no wonder they were having trouble understanding me. I had a 3D picture in my head of the things that we were looking at. They didn't. They just saw them as flat pictures, and they couldn't extrapolate them into 3D. So I mean, just fascinating. At any rate, truly finding the 3D structure is something that we've, that we work on all the time. So here's an updated version of the Orion movie that HST put out, I don't know, 15 years ago or so. And now this one's done with some Spitzer infrared data as well as optical data. And I tried to read the description of how they made it and how they knew where the stuff was. And they don't really tell you. They say it's a combination of data and intuition. It's like, okay. I think it's probably pretty good. They can tell when a front surface of a cloud is being lit up by a nearby star and things like that. So there's some information in there, but I don't know. And then many years ago, back in the early 90s, grad student of mine, Tracy Delaney, and I talked about this object many, many years ago at an MAS meeting, Cassiopeia A, supernova remnant. She developed a way of getting a 3D picture of this supernova remnant in the following way. She said, if there was a spherical explosion, then the things that are moving towards us very fast, if you measure the Doppler shift, will be on the front side. And the things that are moving very fast away will be on the back side, and then sort of zero velocity, sort of in the middle. And so for every little knot of emission, and this was done with infrared, mostly with infrared data from different elements. So you have iron, silicon, oxygen, and argon, a bunch of different elements. For each of them, you can measure the Doppler shifts, the velocities, and then you just put them there in a 3D box. And so she made a 3D image. Let me play this. And this is just, whoops. Don't do those things. Rotating is just hand rotating around there. And that sphere in the center is just an artificial thing to show you that all of these structures were sitting on the surface of a sphere. So this was a great way to get a 3D picture. And so people have used this now in various types of modeling. No, Cassiopeia A, the supernova remnant. It's one of the 3 constellations I know. So you again may want to reconvene the board. Okay. Yeah. Oh God. Michael Faraday, 1845, finds that heavy glass, which is glass which has been doped with various excuse me, metals and stuff, that if you took polarized emission and put it through the glass and looked at the angle that the polarized emission was, as it went through the glass, the angle rotated. And that's what we now call Faraday rotation. The longer the path length that it went through, the more rotation there would be. And so what others have hinted at, and what I've done in the last 6 months or so, is turn this into a 3D tool. That what I'm saying is, if, I'll show you the diagram because it's a little bit more complicated. We can measure how much things have rotated. This is a little subtle, but the question is, if you observe some polarization angle, look at a radio source, we observe polarization angles, how much did it rotate? You have to know where it started to know how much it rotated. But it turns out the effect depends on the wavelength. In fact, it depends on the wavelength squared. So you look at a few different wavelengths and you compare how different they are from each other, and you can figure how much rotation has gone on. What's that? Okay, that's okay. So you shine a light through Caro and you can get okay, cool. Can I do it with other syrups? Okay. Okay, 2 possibilities. One possibility is that this Faraday medium, which all you need is some hot gas and a magnetic field. That's what's the equivalent of Faraday's heavy glass. Hot gas, the electron strip, the plasma, and a magnetic field. Put radio radiation through there and the plane will rotate. But if that cloud is in front of the radio source, unrelated to it, you learn nothing about the radio source by figuring out how much rotation there was. So that rotation often happens from our own Milky Way galaxy. The radiation from this radio galaxy comes to us from billions of light years away. It's fine, nothing happens to it. Then it hits the Milky Way and it starts getting rotated. And it goes through one little patch, it's rotated one way, it goes to another patch, it's rotated another way. We can't learn anything about the source because it's all happening, all the action, the rotating action is happening in the Milky Way. If we're in that situation, this whole thing doesn't work. But if we're in the situation where we're in a clean area of the Milky Way, where it's not doing very much rotation, and if the object, which here is, I've drawn a little radio galaxy here, is sitting in the middle of a giant cloud of hot gas with a magnetic field in it, then we have a chance of diagnosing something, because this side goes through a long path length getting to us, and this side goes through a short length. So I might be able to see that one side of the object, the rotation is just a little bit, and the other side, it's a lot. And I can infer, perhaps, I mean, you have to go through all the possible explanations, that this is an object which is tilted, and one thing is further away, coming through a longer path, and another one is not. So I've tried to ask, how is it that we could determine which of these, how can we tell whether it's a foreground or whether it's associated with the object? And the answer is we've been looking at it wrong. And we have hidden this information from ourselves because of the way we've decided to display it. So this is a picture of one of these radio lobes. So it's just half a source. So the object, the host is off to the left, and jets came out and inflated this big, almost circular looking object. The colors are showing you how much rotation there is of the polarization angle at each place. Okay, so say it again. I got radio galaxy, and then I'm coloring it to show you how much rotation was at each pixel, essentially, each beam. And where it's red, there's been a lot of rotation. And where it's kind of blue, there's been very little rotation. And the question is this something just from a foreground that doesn't care about the radio source? Or is it something that's local to the radio source? So what I decided to do is do the thing like Tracy did with the velocities and say, let me assume that this is connected with a source. And when the rotation is a lot, I'm going to say it's far away. And when it's just a little rotation, I'm going to say it's close. And I'm going to make up what I call a pseudocube. So now I have a cube in space where every little place is put some distance along that third axis of the cube, either far away if the measurement is high, and close to me if the measurement is low. And then I look at it and ask, does it look coherent? Does it look like random garbage, or does it look like a real structure? So how do you view a cube? The easiest thing to do is to make a movie of going around it and looking at it from different perspectives. So that's what you're about to see here, is a movie of that lobe. And there's all these fun little filamentary structures. And I've tried this by taking random Faraday rotation, random colors, and putting it across the lobe. And you don't get anything that looks like these nice coherent structures. It's just a mess. It's just all jumbled up and stuff like that. So this is one indication that this Faraday rotation was probably local to the source. And each little filament radiation is either further away from us or closer to us, and then we can reconstruct the 3D structure. So this is just how I do it, but that's too much detail. And so this is now a front view of the same source we were just looking at. Here now is the polarized emission. And now I'm just going to go to the top and look down. So I look down from the top and I can already see hints of that nice coherent structure, those nice coherent lines. And then I look at it from the side and there's coherent structures. Of course, it's all sort of still mixed up because I'm looking through the whole object, and that's why you really want to look at the movie. So what is a radial lobe? My picture of a radial lobe before was that it was sort of an amorphous cloud of plasma. A jet came in, pumped up this cloud of plasma. There might be some enhancements on the edges because there was some pressure, little shocks, or maybe some turbulence inside. That's not what's going on. These lobes are like a bowl of noodles. That's why I've got the noodles there. That's what these things look like. It looks like a bowl of noodles. So something that has happened inside these radio galaxies to turn them into a bowl of noodles. And we can only see it when this foreground contamination, like from the Milky Way or other things that are in the way, isn't very strong. And most of this rotation is local to the source so that it can actually do this 3D reconstruction. I'm going to skip this one. So it's a little bit more complicated. And the reason it's a little bit more complicated is that if you ask the question, how much did things rotate? And that's what I've quantified here as number 5, how much things rotate. It does depend, so it's an integral, it does depend on this DL, which is just the path length. How far away is it from us? But it depends on the property of the medium. It depends on the density of electrons and the magnetic field strength. If I were to up the density of electrons, the amount of rotation goes up. But that doesn't mean it's further away. That's a separate effect. So there are 3 different things that could change. Sometimes it could just be the real 3D. Sometimes it could just be the magnetic field is changing or the density is changing. So I've had to develop some tests to sort of distinguish between these two. And here's one example. So here we're looking at a source from the side. It's a double source. This is actually Centaurus A. And here's an optical picture of it with some, here's the radio lobes. Here's the dust lane of this giant elliptical galaxy. And here we're looking at it, these radio lobes, I've just rotated them a little bit. And here's the top view. And in the top view, there's this enormous discontinuity, like a giant jump between the jets that are feeding the lobes and the lobes themselves. So here's the jets feeding into the lobes, but it looks like they came from a different place, but they didn't come from a different place. They're connected. Those jets are pushing right into the lobes. So this one is not a distance effect. The movie is not showing you distance. The movie is showing you something else got in the way with a stronger density and a stronger magnetic field and made the depth, made the Faraday depth. Whoops, we've got Trina, we've got the speaker again. But if it's not bothering people, that's okay. At any rate, and okay, and there is something in the way. Okay, it's the galaxy. The galaxy is sitting right in the place where the rotation was more. So it wasn't that the jets got disconnected from the lobes. It's that I put a galaxy right there in that position and it made the depth look different. So part of what I'm working on, I'm still writing up the paper with several different colleagues, trying to show how you can diagnose when is it really 3D, when is it something like an enhanced magnetic field or enhanced densities. And this is just another example of something that I'm in the process of diagnosing. And what's cool is, as in one of the first examples that I said, again, when we look at a picture in the sky and we have these double radio sources, we don't know who's approaching us and who's going away. And that turns out to be important in some situations, but now we have a tool that can tell. And so this movie is just part of the diagnosis that I'm doing to figure out which one's coming towards us and which away. Just comment here without going into the details that I can also diagnose now the magnetic field structure inside things like jets in 3D. Before, all we could do was see the polarization angle in the sky, figure out what the fields were doing in the plane of the sky. With this technique, I can now get that third dimension of the magnetic fields, and that's what people do in order to get physical models. This is, those of you that know Virgo A, M87, this is the jet in M87, and this is the movie around the, I haven't figured this one out yet. I spend nights just dreaming and visualizing this movie, and I haven't figured out exactly what I'm looking at yet. I think that more than one thing is going on, but it's not random. I mean, that's really the cool thing. If this were just random stuff in the foreground, we wouldn't see these beautiful patterns. But the patterns there are telling me there's something physical going on, and that's what I'm trying to diagnose. Okay, we're coming to the end here. So I am now in the process of trying to convince my colleagues, stop doing this. It's not good. You can't tell what's going on, and do this and see if it works and gives you some coherent structures that you can start interpreting physically. So that's sort of what I'm up to, and I'm doing this with all kinds. I'm asking people to send me data, and I'll make movies for them and send them back to you. So that's what I'm doing in retirement now, except the last thing, whoops, where's my picture? Oh, at the very end, there it is. Okay. Yeah, can we turn the lights down? Because this is I am so proud of this picture. I made it this morning. I made one last night, and then I made a new one this morning. And what you're looking at is something from the Legacy Sky Survey. It's a public site. You can get these beautiful images. You just put in the coordinates and you get these images. That's great. That's fine. Magic. And the purple stuff is the radio emission. And there's two rings there. See the two rings? So we're back to the orcs again. The odd radio circles. So this is another one with a pair of circles. And the surprise here, and so I just GIMP, that's what I use for, and those of you that know these image processing tools, this is just an overlay in GIMP. The cool thing is that if you look in the core and ask what's going on here, it's not an elliptical galaxy. It's a pair of spiral galaxies that are orbiting each other and pulling out tidal tails. How they put out this kind of energy to make this giant radio source, we have no idea. One thing you could do is, almost certainly what you need to do, if all of our models are correct, is you need to put a supermassive black hole in each of them, 1 billion solar masses in the center of these spiral galaxies. But our Milky Way, which is a spiral galaxy, has got 1 million solar masses in its black hole. You don't find billion solar mass black holes in the centers of spiral galaxies. So this is a mystery. It's also what keeps me up at night, and I hope it'll keep you up at night a little bit too. Thank you. That's it. No questions about constellations. Okay.
Does anybody have any questions out there? All right, hang on. Let me come over there.
Now's the time that I worry what Lauren was going to ask me. All right.
As a ham radio operator over 50 years ago,
Mhm.
I wonder what frequencies are you looking at? And I'm thinking they probably were two meter band.
Yeah.
You know, from
The telescope that the little helix telescope that I built on the roof was probably 300 to 400 megahertz or so. So 1 meter, or a little short of 1 meter. So most of the radio amateur stuff is in the 2 meter or up band. But for these guys doing moon bounce, they were working at a bit higher frequencies. So that's why I was picking them up.
Related to that, apparently Elon Musk's satellites, along with visually being a problem, are creating spurious radiation
So
Covering all over the band?
yeah, so I just saw an article that we have protected bands in radio astronomy. So we are using much wider bands than the protected ones because that gets us a lot more signal. So we are making trouble for ourselves by going outside of our protected areas. But the satellites are pretty tightly regulated and they can't really transmit signals in those bands. But the study I just saw was they're picking up the internal electronics now. So our telescopes have gotten so sensitive, they're not broadcasting signals, they're just running RF signals through their various equipment inside the satellites, and we're starting to be able to pick it up. So yeah, it's not clear how this is going to play out. It's a problem.
Oh. You have one online? Or no?
I was wondering, are there any other processes that can cause radio emission besides cyclotron and synchrotron radiation?
Yes, yeah, there are. And for the kinds of objects that I've been showing you tonight, there's really no competitor to synchrotron radiation. But there are other types of objects for which these other mechanisms are very important. So you can actually have thermal radiation from hot gas. So when you look at an H2 region, and I think probably even some planetary nebula and stuff, you can get radio emission, which has nothing to do with synchrotron. That's just from hot gas. We call it thermal Bremsstrahlung. Pulsars put out more coherent forms of radiation from like beamed electrons along the magnetic field. And that's not, well, it's sort of coherent synchrotron. It's related to synchrotron emission. What other mechanisms do we have? For spectral line, we have, so spectral lines that you see in the optical are electron levels, nice big jumps inside the atom, but you can also do tiny little jumps from spin flipping type things, for example, and that can give you radiation because there's much less energy involved. So the 21 centimeter line that we use to study hydrogen throughout the universe, that's a completely different mechanism. That's just spin flip, and it puts out a radio photon. So yeah, there's a variety of mechanisms. That's a good start.
Don, I'm curious to tap into these public databases, but I don't know how.
Yeah. Do you have a goal in mind, or you just want to be able to look through stuff?
Certainly, I have various projects in mind. Yeah. Oh, very specific projects.
Yeah. So I would send me an email with just a couple of different kinds of things you're interested in, and let me get you off in the right direction.
Okay.
Okay.
Thank you.
So it's just larry@umn.edu. It's real easy. How did I get that, you may ask? Been around for a while. In physics and astronomy, we had our own computer systems before the university had any. So we were sending emails and stuff like that over the DARPANet and stuff like that. And when the university finally got its system, they grandfathered us in and let us keep our names. So I'm just Larry. And I get interesting emails intended for other Larrys. And I just politely return the mail and go, I'm not the Larry you intended, you know.
So my question is about the polarization angle and the differences. How big is that, and can it wrap all the way around? And if it wraps all the way around, do you see gaps that would be explained by that, where something further away versus something close? Yeah.
So if you think of an angle, it's really continuous, right? It just keeps going around and around and around. Our measuring scheme, we run out of numbers. So we go 0, 360, oops, I got to write 0 again. But it really is continuous. So we can figure out when it's going around more than once if we have enough samples. If you don't have enough samples, you have one here and see how much rotation, another one here and you see another amount of rotation. You don't know if it's done a full flip in between them. And we have a name for those. It's called the n-pi ambiguities, because any pi radians, any number of n pi radians could have happened. So we're very sensitive to that. And we try to get enough coverage so we can track what it's doing all the way and not fool ourselves about what happened in between.
I was just curious, you know, you've mentioned using using primarily radio data, right? Have you gotten a chance to get into, let's say, the James Webb data, the infrared data?
Yeah, I personally am not. I have collaborators who are. I do a lot of X-ray stuff also, but again, mostly with collaborators. But unfortunately, I can't tell you anything about the web. However, there are all kinds of things. Where were the jumbos discovered? You guys know about jumbos? In Orion, Jupiter mass binary objects. Jupiter mass in binaries floating around through Orion. Who ordered that up? And I'm pretty sure that was a Webb thing. So I follow the news like you do for stuff from Webb. I'm just not personally doing it.
I do have a question online. What is the best way to follow your research? Is there a forum I should follow?
Oh my God.
Larry at.
So we have a follow is I don't know exactly. Just Google me. You know, if you Google Lawrence Rudnick, Minnesota, all kinds of things will come up. Previous talks that I've given, things like that. If you wanted the professional literature, we have databases where you can type in somebody's name and find everything they've published. So if the person that's online is interested in actually seeing some of the original literature, then just email me and I'll send a link to the database. They're public databases are run by NASA. I do not, no, I haven't gotten into that. No. I mean, I admire the people that do it, and I've just never gotten into it.
All right.
Larry, I love how you finally retired, so you got some time to get some work done.
Right. Yeah, the pay is gone, but the fun is all still there.
Fun is all in bunches. Congratulations.
Thank you.
Every day, as I work with the little kiddos, I get the question of Pluto. Now, Alan Stern was in the news today. He flew up on Virgin Galactic. He got to do 4 minutes of zero G.
Mhm.
As a fellow IAU member, what do you think of Stern's expressing the idea that, hey, science isn't democratic? We don't do this by vote. So how do you come up with the names of things? Is there a little bit of voting going on? Is there lobbying? Is there arms twisting?
It's a very interesting question. In radio astronomy, the radio galaxies, some of which I've been showing you tonight, we have approximately 6 to 7 decades worth of history from when these things first getting started. And the naming of objects has gotten so complicated and contradictory, and people use different systems, that for the past several years, I've actually been working directly on that issue. And I've gone to conferences and given talks and taken polls and stuff like that. And I've come up with a completely new scheme. And my new scheme, which I've written up and some people are starting to adopt now, is to say we are not going to name objects. We're not going to name them. What we're going to do is we're going to have an object and propose a test. Is it circular? Is it this big? Whatever test you want, a defining test. And if it meets that test, you give it a tag. That's it. It doesn't mean that's what it is. It means it passed that test. And that means that somebody else that looks at that object with a different telescope may give it a different tag. And we don't have to worry about the fact that it's two different kinds of objects. Each tag is very well defined, an objective test. Is it this big? Is it a long, narrow thing? Is it have a spectrum that's this or that? Whatever the tests are, you give it, if it passes the test, it gets a tag. And we will all agree what test was done and the tag, and somebody else can come up with a different test and they can have their own tags. That removes all the controversy because we stop asking what is that thing, and we just ask what tags are associated with it. What tests has it passed? And becomes completely searchable. And it relieves all the strain of trying to make a decision. I tried to come up with schemes in which there were hierarchical classifications, a radio galaxy, a double radio galaxy, a one-sided or an asymmetric double radio galaxy, a bent radio galaxy. And well, do we call it a radio galaxy or do we call it a bent radio galaxy, or do we call it a head tail or a wide angle tail or whatever? We don't, I'm suggesting don't do it anymore. Just assign tags to it, make whatever test you want and assign a tag. And I wrote an article called Radio Galaxy Classification Tags, Not Boxes. And I used the hashtag symbol, which we use in social media and stuff, to indicate to people, because everybody knows what those are. Those are descriptors. They're not exclusive categories. They are a descriptor that this belongs to this group of related concepts. So that's where I am on naming.
It's almost more like an ISO spec where it meets certain qualifications.
It meets certain qualifications and it gets this designation, but it's not an exclusive. It may meet other qualifications for other tests.
Okay.
I wish the open cluster program had that. Any other questions? All right. Well, thank you very much,
Right.
Larry.
And thank you guys again. This was wonderful. Right. And here's how you find a source in the sky.
Yeah, I want to see that. Well, thank you everybody for coming tonight. And for those that joined us at home,